Great to be here. Really fun. Let's talk about how agent platforms are built and where the world's going right now.
And I allowed myself to use this picture here. Is a shift from chopping down trees with a handsaw to chopping down trees with a chainsaw. And of course, it's much more efficient, but the whole ecosystem you need around a chainsaw is quite different compared to a handsaw. You need fuel, you need security, you need a whole bunch of things. So it's quite a big change that we're seeing right now. The tools we're using are becoming much more capable, much more dangerous, much faster. And that doesn't mean that there's going to be mass unemployment, but it does mean that the way that society works changes over the next, well, right now. So if we're going to do these things, if we're going to be using AI, if we're going to be using agents, machine learning, things like that, then built on trust, driven by growth. We need to build trust in these things, because if there is trust, then people take action. And trust is based on three main things. It's what we know, what we do, how we think, and recognizing how the counterpart and the people around us function in those three ways. And for all of those three things, I listed three things. I'll focus on the middle one. I'll focus on how the world functions, evolves. I'll focus on how we can analyze, plan, and execute going forward, and I'll focus on managing our emotional response to these changes. So those are kind of the underlying themes that we're going to be going through. This presentation is not intended to be gentle. It's quite solid. It's quite a mouthful. So stay with me, bear with me. What I'm going to do is I'm going to start at the chip level and go all the way up into intelligent agents, all inside the next 40 minutes from now. So, okay, hold on to your hats, keep your socks on. Let's get into this. The general architecture is to think about the applications as being on the top and the chips, or the CPUs or GPUs, sitting at the bottom, and in between that top layer of the friendly apps we love and the silicon on which this is run today.
I'm sorry, may I just interrupt you for a second? Would it be possible for you to switch to the slideshow mode so that we can see it a little bit bigger? Thank you.
Is that better?
Yes.
Wonderful. Thank you for doing that. So between that top layer of applications and CPUs and GPUs at the bottom, there needs to be a bunch of software, and it is useful to have an understanding of how that software is constructed, because it shows us the opportunities and the vulnerabilities and the risks of all of these systems that we are introducing right now. So there are enormous risks with all of these things and enormous opportunities at the same time. And I'll show you how that works. So let's go back a short period of time. This computer on the right was built before even I was born. And it took 10 or 20 years for this computer to fit inside a pocket calculator from Sanyo, or from one of the Japanese companies that introduced pocket calculators in 1970, 1971. And by that time, IBM had already switched its business to be more hardware, more software and services, as opposed to pure hardware. So that's what happened with this machine. This machine is the same size in cubic meters as and that's the machine that put that machine out of business, by the way. That machine on the right is the first Sanyo pocket calculator that put that machine out of business. The NVIDIA systems of today take up the same space, but they don't fit in our smartphones, or so they would need to be 1 million times smaller in order to fit that inside our phones. Okay, well, 1 million is not very much. 1,000 is 2 to the power of 10, it's 1024. So if you take 2 to the power of 20, then you're at 1 million and 756, I think it will be. So 1 million, say. Great. So that needs to become 1 million times smaller to fit inside our phone. Well, the transistor density is doubling every 2 years, according to Moore's law, and that's still true. It's been true since the 1970s. However, the improvements in chip architecture and temperature management and things like that means that chips, in reality, are doubling in their capability every 6 months. Okay, every 6 months. So that's 2 doublings in 12. So that means that 2 to the power of 20 is 10 years. That means in 10 years' time, that computing capability will be in our phones. And that's been realized by not just this talk together right now, but it's also been realized by many other people. So the Shanghai Cube is a system that does something very similar. And we will see compute power in all the routers, Wi-Fi routers. We'll see them in all the telecom base stations. We're going to see highly distributed, very capable compute capability distributed all across our globe, because computing hardware is going to be very capable, and relative to the cost, relative to the performance, the cost is going to be low. So that's what's coming. It's a new architecture where we have compute everywhere, absolutely everywhere. Now, for that, we need to start thinking through, okay, so how are we going to plug these things in together with each other? Well, step number 1 is that for each physical underlying compute power, we need a virtualization layer so that we can have the same applications distributed across multiple different data centers. And on top of that, we need some place where we put our apps. So our apps need to be split into jobs. Those jobs need to go into some places. The place to put them typically today is in something called a pod. And it means that one digital retail app can be split into places where you just pop the different tasks in different places and execute. Meaning that digital retail app need not all execute on one CPU, it could execute in different countries. And within companies, outside companies, on the edge. So with edge, I mean things such as a water pump might have a GPU, and so that's got its own compute power. Maybe a camera has its own GPU that's got its own compute power, and so forth. So we're distributing apps all over the place. For that, we need a multi-cluster control plane. This exists now. So it's possible to have job scheduling and rules, data orchestration policies where the right things happen in the right place. So if you, for instance, have medical applications, then you might have a rule which says that medical applications or medical data has to stay within your jurisdiction. If that's true, then some jurisdictions will not be okay, and you'll need a multi-cluster control plane where you have data orchestration policies which puts the appropriate app in the right place. All of that exists. And it means that there is a security opportunity and nightmare at the same time. Truly both, truly both. On the right-hand side, I've listed 5 layers of software. One is cloud native, one is using the AWS services. Those 5 layers are replicated across all the different software providers pretty much. And those are the 5 layers that connect the apps to the silicon. And they're built in similar ways and differently. And all of it is vulnerable. And humans are also vulnerable. All of the encryption keys that we used to have in the past, like 512, 1024-bit key lengths, are becoming really vulnerable now because the silicon performance is such that you can do brute force, unintelligent attacks just to open them up. If you look at the current 2048 bit key lengths that we're using right now, they will be broken before my laptop is brand new. So before this laptop comes out of use, the 2048-bit key lengths are going to be broken. And then we get 3072 after that. Great. That means that there's a trade in databases that are encrypted at all of those depths, because you will be able to open those databases later on. If we're deploying this stuff, then those 5 layers are replicated across all the different providers of software. And from a security standpoint, this is wonderful because the surface area for attack is enormous. There's so much sensitivity here, and there is so much strength. So we're going to see some wonderful disasters, but the beauty with this is that things move fast, and there's automatic failover and traffic management. So if you're running something important, then you run multiple clones of the same thing. If one of them falls over, you fail over to the next one, pop that back up, and you fail back over. So incredibly resilient. If you are running an app that you need to upgrade, then you look at the different clones and you replace one of the clones with a new version, and then you replace the next clone with a new version, let it fail over onto those new versions, which means that you have continuous integration, continuous deployment on everything you do. And the multi-cluster control plane will do things both economically and technically optimized. You don't want to run expensive stuff on expensive computers. You just want to be simple. One of the big things that's happening here is that there's a move now from what used to be true a long time ago, like 3 years, where there was a single source of truth in a database architecture. The move now is towards more of a distributed mesh data with Fabric, where you accept that data has a particular degree of truth in it, and you're using distributed mesh to work out roughly what you should be doing. So the word truth in these new architectures is being redefined so that you have multiple truths at the same time. You have models that say different things. You have data that says different things, and you find ways of managing those things. All right, so let's move higher up. Let's start looking at these different models. So large language models, we all know them, we all love them, we all use them. They're kind of simple. So you spend $100 million to make one cut of ChatGPT, and that gives you a 1 terabyte pre-trained summary of the internet. And it's like a friend who is decisive and vague and has a memory cutoff time and is a little bit drunk, maybe, I don't know. But it's a very, very intelligent friend. That's what we get for $100 million. What's happening now is that people are making lots of these LLMs for specialized tasks. So instead of just having one big mothership LLM, people are going to be using many LLMs that sit side by side in libraries. And you then orchestrate all of those LLMs down into the different places where you want to use them. The LLMs are also being RAG strengthened from below so as to give them much more capability. I'm sure you've seen that. And what will happen is that we will talk, and our talk will be converted to text. We'll go into LLMs. The LLMs will be doing lots of clever things, then convert back out to text and then talk back to us. So talking systems are coming also for factories. So this woman on the top right here is wearing 5G capable glasses that are available straight from the shop right now. She can have a conversation with a client and hear the question, do we have blue M9s in stock? And immediately answer, yes, we have seven of them in Munich, because her glasses with voice tell her that there are stocks in Munich, 7 units available for sale. So voice-based factories, voice-based environments are coming. Okay, so what will that look like? Well, ultimately, we'll have a corporate brain in the middle for each entity, whatever that is, for each company, if you wish, if you want to call it that. And on the left-hand side, we'll have these things called humans who communicate with this corporate brain. And we'll also have intelligent agents on the left communicating with this intelligent aid. The brain itself is like an agent engine with models and plugins and everything else. And it is a proprietary ecosystem of specialized machine learning AI agents, which is the corporate brain that this company operates off. On the right-hand side, there are bucket loads of models that enable this corporate brain to function. Those corporate brain things split into three things. One is machine learning, one is AI as we used to know it a long time ago, like 12 months ago, and one is agents, the way that we know it as of November. So let's start with machine learning. We're all familiar with this famous quote, which Einstein didn't say exactly, but like William Shakespeare said, most of the quotes given to Albert Einstein and Winston Churchill are actually not accurate. I read that on the internet, so it must be true. The machine learning stuff is the very opposite of Albert Einstein. It means that the definition of sanity is that we try to replicate what we've done before. So we end up with decision trees using machine learning, and we end up with decision forests using that. And we have development environments where it's possible to develop really advanced and good machine learning systems. This is bread and butter, and a lot of the stuff that we call AI today is actually machine learning. This is unbelievably important. It seems not fancy and so forth, but it's really, really important stuff. When we move into AI, we shift into this discontinuity world. It's a different way of thinking about this. And my very good friend, Professor David Zeitlin, wrote a book, which I think is so insightful about how to think about this. So we need to use the structure of our perception in different ways than we have done before. He's an anthropologist, and his thinking is applicable to agents. That's quite fun. Let's look at the AI models. On the right-hand side, you can see a pink line and a turquoise line. The purpose of those is to show that with two really super intelligent models, we get two different results. AI models typically give different results. They are similar. You decompose different, smooth, regress, fit it all back together again, and boom, bingo, there you are, you have a result. But it depends on what you're trying to do. So you'll have different models for different things. Facebook has made its profit model open source, which is extraordinary. So this is all about clustering. So if the app you want to develop is all about clustering people, then or things, then this is really powerful for that. This is used by the oil industry for forecasting demand, which is a bit tricky right now, to put it mildly. This is great for any system where the underlying observable is not directly available to you. So you do layers of models, and this is great for finance and so forth. So you have different models that you can use. All in all, you need a data science development environment that spans all the way from little things like cameras and Internet of Things, things into really large projects. And you want to be able to develop all of that from one place, and you can. So all of that stuff exists today. What we end up with is something where a bit like a big orchestra, Berliner Philharmonica, or we end up with different instruments doing different jobs to create the effect that we want. And we have an agent development kit. Now, I use this picture here from 1950. This was for sale to children in the United States in 1950. And the box includes uranium-238, so it's really nice because your kids can do atomic level experiments in their home. There's a handbook as well because it's a bit difficult. That seems a bit crazy, but these new agent development kits that are coming out are like this. So in 1941, 42, when Niels Bohr and Mr. Oppenheimer and so forth, when they developed the first atomic bomb and tried it in Arizona, they didn't know if the atmosphere would ignite or not. So there were a bunch of them. A couple of them thought that the atmosphere ignites. Some of them thought that, hey, let's do it. In the end, they decided, okay, let's do it. Boom. And it went bang, and the atmosphere did not ignite. And we were lucky. Well, I mean, if they would have been wrong, then we wouldn't be here. Okay, that's the way that rolled. So the level of risk that people took back there was absolutely enormous. The agent developments that are happening right now are at this level in relation to humanity, and they are available. All of this is available. So agent development environments, all the way from little things to big things, are fully available. You can build agents that are pretty much impossible to stop, because you can make them self-deploy in such a way, as per the architecture we discussed earlier, that you just can't whack-a-mole, you just can't find them. So they'll just keep running. And one wonderful example of this is a technology called OpenClaw. Now, since this was launched in November, OpenClaw is the fastest developing technology so far, without any restrictions. Okay, that's an incredible statement. Launched in November, it's been copied by bucket loads of people already, so there are lots of different claws. Essentially, what these things do is they act on your behalf, and that's the general idea. And you can build an architecture where you have one main OpenClaw instance, and then underneath that you have different OpenClaws. Each OpenClaw can then be given access to different skills. So those skills, for instance, can be the ability to connect to LLMs. So on the laptop that I'm presenting from now, I'm running OpenClaw, and it's connected to Claude, it's connected to ChatGPT, it's connected to, oh yeah, I've downloaded 1 terabyte of LLM onto the laptop as well. So it's using that as well. So it's got different LLMs that it can use for different purposes. And it's learning which one to use when it makes most sense to do what. My user interface into my agent is WhatsApp and Telegram. So I write messages into Telegram and into WhatsApp, and I talk to it just like if it was a person. And OpenClaw does things for me. So I needed to, for instance, sync my photographs with iCloud. So I asked it to, please, can you do that? So it set up everything for me. To make a PowerPoint presentation and email it to one of my friends. So it did that. So with these agents, instead of asking it questions such as, what time is it? You say what your goals are, and based on your goals, it will execute on your behalf as if you were that agent. And at the moment, these agents are pretty much experimental, such as me playing around on my laptop, but they're also in production. So there are laws in China today that say that by 2027, 70% of agents shall be autonomous. So autonomous agents are coming really quickly, and they will be indistinguishable from us. OpenClaw was launched in November. NVIDIA has already incorporated OpenClaw in its core platform. So they call it NemoClaw, and they've put some security things on top, which makes sense. And but this just shows how quickly this is moving right now. This presentation would have been quite different, was quite different on the 25th of January in Adelaide compared to now, because of these agents. And we need to think about these agents being deployed in a network, and there are protocols with which agents can communicate with each other. So if we have one agent, they need to be able to talk not just to me because I'm slow, but also to each other because they're fast and they work 24/7. And we need to be able to build networks of agents, and we need to be able to build hierarchies and architectures of agents. That's all possible. These agents, when they start talking to each other, they can go nuts because they talk quickly. So we need resource allocation and prioritization so that we understand which agents is sucking up what bandwidth, if you wish. And the agents, like human beings, will disagree. So we need a clever architecture whereby we have policemen agents that resolve conflicts and so forth. And all of this needs to be done inside a governance architecture, and it can be, because it of course makes sense that if agents are handling, say, medical data, then there are things that the agents are allowed to do, things that they're not allowed to do. So designing this with governance in mind from day one saves very much time later on in any project. If you introduce governance at the end as an afterthought, then you'll have to re-architect everything, I assure you. So think about governance up front. Think about all of those 4 elements when you build networks. So multi-agent communications and so forth, all the way, those 4 elements at the top are important. And when building these systems, the trick is to build many small agents that do clever things respectively, and then let them communicate with each other using these protocols. The reason is that in these systems, if you have one set of truths on the left and one set of truths on the right, these systems are incredibly good at filling in the stuff in the middle. And that's where hallucination comes from. So to prevent hallucination, it's really important to think through the architecture of the agents so that the agents do what they're supposed to do, and the governance sets limits for what they're supposed to do, and they don't do other stuff, because in that case you get a mess. Okay, good. Testing, coding support, DevOps, DataOps, all of that goes with this. So testing this, exactly which version did what, certainly not simple stuff to do. And the way that we think about data as a whole, data is a continuous flow. So on the left-hand side of this picture, you have a whole bunch of data coming in from different places. It's being managed and made into data artifacts that can actually be used. In the middle, there's a whole bunch of stuff going on with algorithms and models and LLMs and agents and so forth. They come through a different funnel and become artifacts that are ready to be trained and to be tuned. And then at any point in time, we use the current data artifacts, the current model artifacts in order to generate something. Understanding exactly how this works in terms of model versioning and so forth is critical, because if people come back and sue us in 2 years' time, we need to be able to say that we were running version 6.1 or 2.1, and all of these, we need to be able to recreate that for a full kaleidoscope in order to find out what happened. Everyone is out of date. I think there are a couple of worthwhile publications to read in the world. Financial Times is one, Frankfurter Allgemeine in Germany is one, Helsingin Sanomat, I don't know, New York Times maybe. So the couple of publications are worth reading. Most of media is not worth reading. And it's difficult to find out what to read. But even a fine publication like Financial Times, The Economist as well, they're out of date on all this stuff. So when they talk about coding these systems, they print pictures such as this one on the right, which shows where people spend money on coding environments. And it's totally wrong, because the majority of the coding that's happening today is with IDEs that is with development environments that are for free, the open source stuff. So, and none of those models that we're looking at on the right-hand side are available in China, So this picture is deeply misleading because it's too US focused. And that's because the wonderful people who wrote the article with this picture are out of date. Why? I recommend that you read this book and do this quiz if you want to check if you're out of date. It's shocking. And this, from a human perspective, this book is, in my opinion, the best way of learning that we are out of date in the way that we think and with the knowledge that we have. It's a wonderful, wonderful, wonderful book. Here's another picture on the left-hand side. Again, this is misleading. This shows the stock valuations of a bunch of US companies. The fifth biggest company is Amazon. Amazon alone has a bigger stock market valuation than all of the US energy business, all of the oil business. One company, number 5, is bigger than all of the oil industry, just to put this in perspective. But to call this a picture of the tech stocks is deeply misleading, because it ignores what's happening outside the US. There's so much action in places such as China. It's a race. It truly is. Everyone's spending money. On a personal level, I'll talk more about this slide next time we meet. But on a personal level, there are some really big implications for this. We can see what the dynamics of where this is going to go. We'll talk more about how difficult it is to innovate within companies as well. And I've done a lot of work on this, benchmarking against companies like Hewlett-Packard and so forth. So ultimately, innovation in companies is very difficult. Big companies are struggling like crazy right now to innovate in this space. On a personal level, what do these agents mean? Well, the agents mean that we can respond much more quickly to anyone who asks us any questions. So great. So my agent can answer on my behalf and whatever. That's insane, and that's where we're going. So I've worked on Wall Street in New York. And one of the key things about working in that environment is that you need to respond really quickly to whichever situation that you are aware of. And it's more important to respond quickly than to be exactly right in that environment. And if you don't, then people will take your clients. So either your colleagues will take your clients or your competition will take your clients. So speed is everything, and speed gives you more pay and more promotion. And it's an incredible thing. So from a human perspective. So doing things really fast instead of taking care of the things that are really important is something that we will see more and more of. And availability kind of becomes our primary value. And there's some really deep human things about that. Let's talk about. I mean, Katarina and I spoke about some of these things earlier. This changes so many things. From an industrial standpoint, let's look at digital retail. So here's an example of a panel that you can build for digital retail. A long time ago, like 10 years ago, it would take 30 people 1 year to build that panel. Now it takes 1 week, 1 person, including testing, to build that panel. So that's different. Why? Because we're using all of these agents to do these things. If you want to do personalized voice intelligence, where customers can talk to the shop about the different products that are in the shop, sure, no problem. So this, including voice interface and everything else, a month, 5 people. Dynamic pricing, we're going to see more and more of that because elasticity modeling is coming into this. So we will be seeing agents doing the elasticity modeling throughout. Physical behavior, smart city. Smart city is going to go crazy with this technology. It's going to be really, really great and scary, but it's a weird thing. I don't know what's good and bad about this. What I do know is that society is changing right now. And to the extent that we don't believe that, then okay, fine. But the discontinuity has already happened. The discontinuity has already happened. It's taken a while. It's taking us a while to realize that, and that's because of that book I talked about earlier. But the discontinuity is already there. This is more about smart city and grid load balancing for energy and more smart city stuff. Autonomous supply chain. I think supply chain is super important. Okay, so how about supply chain that has no humans involved? Because agents on all sides are going to be talking to each other using these agreed protocols that have now been defined and are now in production. So we'll see agent-to-agent supply chain management with chains of different agents, where different agents are under control of different people. And loads of challenges with that, because to some extent those agents will be owned by companies, and to some extent those agents will have been quickly deployed by an engineer who's put it in a personal GitHub account. Okay, that person leaves. All right, now we have agents acting for the company that are actually not part of the company. How does that work? Where's the intellectual property and where is the liability? These are enormous implications for all of these things. If you're looking to build houses, big construction sites, build for rent, build for selling, for purchase, then you have a challenging situation with long development cycles that are capital intensive. And you need to work out the inventory risk ratio and match the type of building that you're building with the cohorts that you're targeting and the monetization models that go with that. So all of that needs to be modeled, thought through, And it needs to be real time because people change their mind all the time. And if we look at the world over the past 2 months, I think you agree that having real-time modeling of exactly what's going on kind of makes sense because things can happen quite quickly. And when they do, you need to change the way that you're I mean, should you really be building right now? That's quite a challenging question. I'm not answering the question. I'm saying it's difficult. And the KPIs for a system like this become gross development margin, absorption velocity of the real estate that you're developing, and the capital turnover efficiency so that you can build more. This can be done. So all of the different elements of the picture on the right-hand side ought to be built real time with agents. And wow, so what does that mean for us? Well, it makes sense to learn this stuff. How we learn this stuff, I don't give advice. And when it comes to trading, Star Trader never gives advice. What Star Trader does is to make extraordinary systems available for normal people to trade. And then people trade at their own risk and benefit. So each client has to be fully accountable. And this applies 100% with how we as individuals approach this. Makes sense to think built on trust, driven by growth here, because step by step, we need to understand how these things work. One way of understanding it is by going to YouTube and watching a bunch of videos or listening to me. A different way of understanding it is by getting your hands dirty. And you don't need to be a software developer. You can use ChatGPT to guide you into the installation of an agent. You can use the agents that already exist inside Claude. My point is that these agents are really something, and they really do change the world. When we bring those things into mission critical environments, we need to be accountable. And that's why I use the example with the manual saw that you operate with one hand, which is relatively safe, and my beloved Husqvarna chainsaw, which is a wonderful machine, and it's really fast. But I need to understand when I'm using my chainsaw that I have some governance to think about. I use my steel toe cap boots, and I'm careful. And I think about whether I have oil in the machine and whether I have fuel in the machine. And I'm careful. I'm still very fast with my machine, but I'm careful. I'm accountable. And this is very similar. So I use Claude technology, as I said, myself, but I don't ask my Claude to, come on, clean up my email. I have too much email, because in that case, Claude will delete all of the email accounts I have, because that's exactly what I just asked it to do. It's a bit like the film Terminator 1, where the Terminator shoots a bunch of people, and or was it Terminator 2 maybe? And the kid says, you can't just go around killing people. And the Terminator says, why not? So it's quite kind of similar with these agents. They don't have common decency. So we need to be accountable when we instruct them to do things. However, understanding these really does make sense. Well, thank you for taking the time to listen to this presentation. And thank you, Dr. Professor Katarina, for making this whole event happen. I think it's really quite incredible. You can connect to me on the left here on LinkedIn if you wish. And as you can tell, this was hurricane speed, very fast, 45 minutes. And please do, let's have a conversation right now. We'll meet up in 2 weeks' time, I think, Katarina, and
Yes.
we'll be able to have a more full conversation about this. But I open the floor. What do you think? Is this fun? Is it scary? Is it both? What are your thoughts?
our productivity will increase a lot. This x-axis is the productivity increase since 1990, and the y-axis is the change in the number of jobs. Will we want that many cups of coffee? Some things will be flexible, some things will not be flexible, so let's see how that rolls. Directly after this video, you will see what we've done in software in 2 weeks by one person up to a production-ready product.
Placing a prediction is simple. Users just need to connect any Web3 wallet with a sufficient balance, for example, MetaMask. Then they choose a prediction, such as, will the gold price be above $5,004 or not? The process is simple. Just press yes or no. After selecting an option, the user enters the amount in USDT and confirms the transaction in their connected wallet. The prediction is then placed. Users can review all their active predictions in the Positions section. After placing a prediction, we also notify the user that an auto-hedge trade has been opened. This trade can be unlocked and managed easily, allowing prediction market users to transition into CFD trading.